Welcome back, Dr. Schoffes here. So we just finished discussing a number of nucleophiles and how we can add more functional group interconversion by changing a ketone or an aldehyde to something else. This segment has a special subsection, so I will spend some more time in 19.10. This section is concerned with converting now carbon-oxygen double bonds into carbon-carbon double bonds. It's a very famous reaction known as the Wittig reaction, named after this famous dead chemist who happened to be German. It's a very important reaction, and here we're talking about carbon skeleton modification, something that's addressed towards the end of the chapter as we're looking at synthetic aspects. So this is ketones and aldehydes are converted to an alkene. We have a double bond. So here we are, carbon-carbon double bond. What should we remember about this? The Wittig reagent is a phosphorus ylide compound. Here, ylide refers to a unique constellation within the structure. A carbon atom is going to act as a nucleophile. We see this in the drawing. See how now our accounting of electrons and the electron flow and mechanistic descriptions is going to help us to guide in terms of the possible transformations in a stepwise fashion. Ylides are overall neutral, but these compounds contain something that is negative and something that is positive on two adjacent atoms, as shown here. We have the possibility of actually increasing through resonance, forming a double bond here. Now, you might wonder, can I have this many bonds around phosphorus? This is violating the octet rule. You are correct, and yet we can still have it because phosphorus has additional d orbitals. But it's good to remember both these forms because they can help us with the mechanism, but also with the visualization. In order to understand what is happening in these transformations, I'll give you a heads up as to how I like to think about these overall transformations. We have, let's say, a carbonyl group on this group. I'm just going to pick acetone. So there are two methyl groups. It's also symmetrical. And you're basically replacing a carbon-oxygen double bond with a carbon-carbon double bond. And the side product for this, I'm sorry, let me just undo this. The side product for this is something that's actually quite annoying when you have to work with it because it's a side product that's very difficult to remove from a reaction mixture. This is triphenylphosphine oxide is going to be your side product. Triphenyl, then phosphorus, and as a double bond to oxygen. I'm just going to leave it condensed here. Triphenylphosphine oxide is a side product. And voila, what have you done? You have now created a new carbon-carbon double bond. Let me fill in the rest. Here are the two methyl groups. Here are the two hydrogens. Okay, so I can draw out the carbon. I don't have to, so this is a skeletal drawing. So just remember that, again, in a way, this is kind of a condensation reaction overall, similar to eliminating a small molecule of water, but here we're more specialized, and we're losing triphenylphosphine oxide as a side product. The mechanism proposed in here is a 2+2 cycloaddition reaction. This goes back to our conjugated compounds chapter 16. Looking more closely, you can now see the mechanism. You may want to pause again. Take it in, maybe take some notes, label it. Do you see the electron flow? Here we are, 2+2. We could also think about this as a carbon-oxygen double bond, and then having our phosphorus compound and double bond to carbon. Here we have the two hydrogens. We have three phenyl groups, which I'm going to condense in. Phenyl, 3. Now you could think about this as also something like this, right? Let me just undo this. Undo. Thinking about this as 2 plus 2, like this. There's another fancy word, oxaphosphatane, a 4-membered ring, carbon-carbon, phosphorus, oxygen. It's weird, it's unusual. Yes, it is. It's oxaphosphatane. And then we get our alkene, and here it is, your side product. It's very difficult to remove via chromatography, calm chromatography, when you're trying to purify the compound that you wanted to synthesize. All right, formation of especially stable triphenylphosphine oxide is the byproduct, and that is what drives this reaction. Here we now see the summary of where do we come up with our Wittig reagent. Let's just start focusing on this part of the slide. Remember, here's the Illet form, here's the double bond form. This is our Wittig reagent, 2 possible resonance structures. How do we prepare it? In a 2-step procedure. Remember halides, you actually saw this in Orgo 1, nucleophilic substitution, SN2, triphenylphosphine, displacing the bromine. Now we have, instead of a carbon-bromine bond, we have the carbon-phosphorus bond with the 3 phenyl groups. There's a positive charge, which makes this acidic. This hydrogen can be plugged off with a very strong base. This is also known as butyl lithium. Butyl lithium. There is a negative charge on that carbon. It's not happy there, so it's going to look to plug off a proton wherever it can. And now here we are. We have a negative charge on carbon, positive charge on phosphorus. Primary halides are more easily converted into a Wittig reagent than secondary halides, when we can sometimes also have side products. And we're not done yet with carbon nucleophiles. As we're looking through this, the Wittig reaction is very useful to install the carbon-carbon double bond by wherever the carbonyl group is. We're now focusing on the stereochemical aspect. Just a little bit here. It has to do with alkene stereochemistry. You may remember that alkenes can be cis. Another label was trans, so it has to do with disubstituted alkenes and where the 2 R groups are on the different carbons. If you have 3 or 4 substituents, you also learned how to categorize them into the Z for zusammen in German, which means the same side, and E standing for German entgegen, meaning opposite sides. Okay, so synthetic chemists love controlling reactions. The Wittig reaction is stereoselective because the Z alkene is favored. Can we see that in the structure? Here we are, carbonyl group replaced with double bond. We have a phenyl substituent and a methyl substituent. And even though you might think, well, isn't that sterically crowded? Yes, it is, but nonetheless, we're favoring the Z isomer. They need to be on the same side in the final structure. And we're not done yet. There is something else that we can consider. We now get to use our electronic insight. Remember, electron withdrawing groups, classification. It helps us here as well, as it did with the conjugated systems and aromatic systems, understanding the electronic aspect. Now, under these conditions, we will favor the opposite selectivity. We get the E alkene. If we are now modifying the reagent, we go to a structure in which we have the substituent from the carbonyl group on one side and then this ester group on the opposite side. Okay. And here is another example. So what are our electron withdrawing groups? Let me just highlight this real quick. I'm going to use this blue here, electron withdrawing group. Well, it's this one, ding, 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 and then this one. And remember how I explained that whenever we have something connected that has a multiple bond, an alarm should go off that this is an electron withdrawing group. Same can be said for this phenyl group that we see. So just by modifying the type of Wittig reagent that we have in here, introduction of electron withdrawing groups will control the E stereochemistry as the major product. And then synthetic chemists are happy for having made selectively or having gotten a higher yield of a wanted product. All right, one more twist to this. The Horner-Wadsworth Emmons reaction, also abbreviated as HWE. Horner is a German chemist, Wadsworth Emmons, British. So the reagent is very similar, but we now have stabilization. Stabilization, wow, we can now think about resonance forms. So as we're looking at the structures, so this is what we just talked about, Wittig reagents. They had a triphenyl phosphine component, P for phosphorus and 3 phenyl groups. If we have now resonance stabilization with an ester group, so here it is, ding, 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 this can take an electron density, so you can formulate resonance structures there. But for now this reaction, what's going on here? What's the difference? Take a look at this. Do you see the difference? So Horner-Wadsworth Emmons, here we are. Instead of having triphenyl phosphine component, here we have phosphorus with a double bond to oxygen and 2 alkoxy groups, in this case methoxy groups. Okay, this is known as the HWE reagent. It is resonance stabilized, and it is a phosphonate ester, and it is a carbanion, a negative charge here. I used my ChemDraw application to basically draw some additional structures here. This structure, I've kind of semi-condensed it here, okay? The focus is really on this negative charge. And if you have trouble understanding this, and chapter 2 talked about formal charge calculation, I've also gone ahead and redrawn the structure, now showing that there is a carbon-hydrogen bond. Remember, we don't often show them because we're used to skeletal drawing. They clarify it and the structure and give a better overview. And then how do we get from here to here? Well, it has to do with, there used to be 2 hydrogens, and now we use a base. So a base, whatever, so the base, dot, dot, I'm going to use a negative charge on here as we're drawing the mechanism. It's going to plug off a net proton, and then that, I'm going to just swerve this a little bit out. This bond here becomes your free electron pair, and that's why there's a negative charge there. Okay, so I just wanted to clarify that with some additional structures. So an example of an HWE reaction, Horner-Wadsworth Emmons is, it gives you E alkenes as the major product, and similarly to the stabilized Wittig reagent. So here's the transformation. Remember, it takes 2 to tango, delta plus. Here we have our full negative. The arrow is going to come over here, and that's how all of this starts. Just to get you started, but oops, shame on me. Make sure you have all the electrons. It's a good habit, and it keeps you out of trouble later on. So here's the special reagent. E is the major product, and we, depending on the solvent use of Lewis acid, we can also affect the stereoselectivity for these 2 very specialized carbon nucleophiles in a Wittig and a Horner-Wadsworth Emmons reaction. So now looking at the synthetic aspect, taking a big picture view, what does it give for our synthetic toolbox? Retrosynthetic analysis means we're using these kinds of arrows. Notice how they're different. It's going back. If I want to make this alkene, I can now think about, there are 2 ways to make these, to make this molecule. This is your target molecule, also often abbreviated as TM versus SM, starting material. But that's, what starting material are we going to use? You can first break it down, squiggly line. So put the carbonyl character on the left-hand side, and then the Wittig reagent on the right-hand side. Although I'd like to actually reverse this. I'd like to draw it as CH2, and then having the rest of the structure here. So I'd like to reverse that. Let's say CH2, hold on. Almost there. So this is my phosphorus. And then we have the 3 phenyl groups on here. Okay. All right. So ketone or carbonyl character left-hand side, phosphorus reagent right-hand side, or we swap phosphorus reagent left-hand side, carbonyl group right-hand side. 2 routes possible. Now, and then also remember how we can make this from a halide, but going stepwise backwards is the starting point. What do we have to pay attention to? Which route is going to be better, number 1 or number 2? You can pause here. Do you have any ideas? Well, remember how the Wittig reagent is best made when we have a primary alkyl halide. This one here would be made from a secondary, this one here from a primary halide. So here we are in detail. Route 1, methyl halide is needed. Methyl halide, methyl bromide, methyl chloride. The 2-step procedure. This as the nucleophile, remember, SN2 reaction. Second base, plug off that proton. Here we are, and get our reagent. If we had to do it with this starting material, now we have a secondary halide. That's going to complicate the reaction, so this is not good. Route 1 is definitely better. So yay, route 1. This is going to be a reaction with good control and likely really great outcomes in terms of yield. So that's kind of the thought process you need to go through when you're analyzing synthetic routes. And so overall synthesis, here we are, methyl iodide, 2-step procedure, Wittig reagent, carbonyl group, alkene, done. And you can practice with additional questions.